Imagine you have two bags placed in front of you, bag A, bag B. Bag A has three red balls and one green ball. Bag B has one red ball and three green balls. Now suppose someone randomly picks a ball from one of these two bags, but he does not show you the color. Now can you tell the probability that this ball came from bag A? That's your question number one. Question number two. Now suppose he shows you the color, that is a red color. So in other words, this is the additional information or evidence provided to you. But you still do not know which bag this red ball came from. Now, can you tell the probability that this ball came from bag A based on this new evidence? Is it the same as before or does it change? And above all, why? These types of questions are answered by Bayes' theorem. This session is about Bayes' theorem. By the way, the answer for this is 50%, and the answer for this one is 75%. Suppose we are given two events, A and E. Based on these two events, we can have two conditional probability. The first one is probability of A given that E has happened, or probability of E given that A has happened. Let's do this one first. This one tells me the probability of A given that E has happened is equal to the probability of A and E, which is this overlapping region, divided by the probability of your E, which is this region right here, the whole region. Okay, now the probability of E given that A has happened is equal to the probability of E intersection A. In other words, probability of E and A, which is this overlapping region, divided by the probability of your A, which is this region right here. Now, from this expression, I can find my probability of A intersection E. That would be equal to the probability of A given that E has happened. I'm just rearranging the terms times probability of E. And likewise, from here, I can derive my probability of E given that A has happened equals to probability of E such that A has taken place times probability of A. Now my A intersection E is same as E intersection A. In other words, probability of A intersection E is same as probability of E intersection A. So I can equate these two equations right here, these two expressions. Equating these two expressions, rearranging the terms, you get this formula right here. This is your Bayes formula. Now this formula, it tells you how you can update your probability of A after you have seen the evidence E. After that, this becomes probability of A such that E has been observed. This one is called prior probability because this probability is before you have seen the evidence. This is called posterior probability because this is the probability of A after you have seen the evidence E. This one is the new updated probability of A. So this is the updated. Bag A has three red balls and one green ball. Bag B has one red ball and three green balls. Now suppose someone randomly picks a ball from one of these two bags, but he does not show you the color. Can you tell the probability that this ball came from bag A? That's your question one. Question two. Now suppose he shows you, he tells you that this is a red ball. This is the additional information provided to you or another evidence given to you. But you still do not know which bag this red ball came from. Now, can you tell the probability that this ball came from bag A, given the new evidence? Let A be the event that the ball is selected from bag A. And let R be the event that the ball selected is a red ball. So this is my evidence right here. So let's do question number one first. You have to determine the probability that the ball came from bag A. This right here. Well, there are only two bags, bag A and bag B. So the probability that your ball came from bag A is 1 over 2. In other words, it's 50% chance. And this is your answer right here. Probability of A is 50%. Okay, now let's do question number 2. You have to determine the probability that the ball came from bag A given that it is a red ball. This is a new additional information provided to you right here. Well, in order to solve this, I'll be using Bayes theorem. This right here. In this case, my E, which is my evidence, is denoted by R right here. So this is my formula that I'll be using. Probability of A given that R is equal to probability of A times probability of R given that A divided by probability of R as my evidence. So let's calculate our denominator first. I'll be using total probability law over here. Now, let's do this using Venn diagram. So your red ball, it can come from bag A or it can come from bag B. So your red actually has an intersection, it's intersecting both with A and B event. So the probability of R would be equal to the probability of this region. So that would be my probability of A intersection R plus the probability of this region. That would be probability of B intersection R plus probability of B intersection R or B and R. And we know how to solve this one using multiplication rule. This is equal to probability of A multiplied by probability of R given A plus, and same thing with this, I can actually rewrite this using multiplication rule. That would be probability of B times probability of R given that B. This is nothing but my total probability law. Okay, and now we substitute our values. So probability of A, what is the probability that the ball comes from bag A? Well, there are only two bags, bag A and bag B. So the probability that it comes from bag A is going to be 1/2. So this is how I come with 1/2. Now let's look at this one, probability of R given A. In other words, the probability that the ball is red given that it comes from the bag A, which is right here. Now, how many red balls do you see? There are 3 red balls. And how many total balls are there? 4. So the answer is 3 over 4. So this is how I got 3 over 4 over here. Plus, now let's look at the probability of B. What is the probability that the ball came from bag B? Again, 1/2 because there's only 2 bags over here. So it's going to be 1 over 2. Now, what is the probability that the ball is a red ball given that it came from bag B? Well, how many red balls do you see over here? There's only one red ball, this one right here. So the answer would be 1 over 4. And this is how I got 1 over 4. So substitute your values in there and your answer would be 0.5. So the probability of getting a red ball is 0.5, 50%. Now let's try to determine this one right here. Probability of red ball given that it is from bag A. Well, that's easy. We already done that. That would be 3 over 4, right? There are only 3 red balls over here in the bag A. So the probability of selecting a red ball is 3 over 4. Now, substitute all these values inside your formulas. We know a probability of A, which is we just calculated a minute ago. So substitute all your values in there. I substitute my values. And the answer comes out to be 75%. So conclusion. Initially, there was a 50% chance that the ball came from bag A, which was right here. Let me just remove everything. All right. So initially, there was a 50% chance that the ball came from bag A. Now, after seeing the evidence that the ball was a red ball, your probability changed to 75%. Now, a 75% chance that the ball came from bag A. Suppose 1% of the people in the population, they have a certain disease. In other words, probability of a disease is 0.01 in a population. And there is a test. It detects the disease correctly 99% of the time. In other words, the probability that the test result is positive given that the person has a disease is 0.99. Also given to you is that the test, it gives you a false positive 2% of the time. In other words, the probability of test result giving you positive, given that the person does not have the disease, is 0.02. Question number 1. What is the probability that a person has the disease before any testing? Question number 2. What is the probability that a person actually has the disease given the evidence that the test result is positive? In above, my D is the event that a person has the disease. So D over here, that's what it represents. P positive over here, which is this right here, this is the event that the test result is positive. Now let's do number 1 first. The probability that a person has a disease before any testing is already given to us right here. So the answer for probability of disease is 0.01. Next one, we are provided new evidence that the test result is positive, and I have to determine probability that a person has the disease given that the test result is positive. So this is my evidence. I'll be using Bayes formula right here. In this case, my A, this would be my D, disease, and my E would be my positive. Positive. So rewriting that expression, this is the final expression I get right here. Let me remove everything now. All right. So over here, I have to find PD. Well, that's given to me already right here. I have to find probability of positive given that person has the disease. Well, that's also provided to me right here. Now, what about this? Probability of positive. Well, that's not given to me directly, but I can determine that using law of total probability. So I can divide my whole sample space into two regions. Well, the person either has a disease, right? Or the person does not have the disease. That's what the C means, by the way. It's a complementary. Now, in this case, a person comes back positive, so he can fall in either one of the region. So I'm going to call this thing as positive right here. So the probability that a person is positive is equal to the probability of this region right here, which is the probability that a person has the disease and the test result is positive. So this would be probability of person has the disease and the test result is positive. Positive plus the probability that a person does not have the disease and the test result is positive, which would be the probability of this region right here. So probability that the person does not have the disease and the test result is positive. This is my total probability law, by the way. Okay, now we can solve each one of them separately. This one, I can use my multiplication rule. So this is equal to probability of disease multiply by probability of positive given that a person has disease plus then same thing with this over here. This one becomes probability of disease times probability of person having a positive given that he does not have a disease. Now I can plug in my numbers. Probability of disease is 0.01. That's given to us. Probability of positive given the disease is 0.099. That's also provided to us right here. Probability of person not having the disease. Well, probability of disease, I know the answer is 0.01. So the probability of having not the disease is going to be equal to 1 minus 0.01, right? And the answer is 0.99. So the probability that a person does not have the disease is 0.99. I derived that using probability of disease, which is right here. Okay, and the probability of person being positive given that he does not have a disease is 0.02. Again, this is provided to us. Plugging your numbers and your answer comes out to be 0.0297. Now substitute all these values in your expression right here. And I'm substituting my values and my answer comes out to be 0.333. Conclusion, initially the person had 1% chance of having the disease before he saw the evidence of the test result. But after he saw the new evidence in the form of the positive test, the probability that a person actually has a disease, it went up to 33.3%. Suppose in a factory you have three machines, A, B, and C, and they produce items and certain percentage of them they are defective as shown in this table right here. So machine A it produces 25% of the items in the factory. Machine B produces 35%, and machine C produces 40%. When you add them all together, the answer is 100%. Now, machine A, the items that it produces, out of those items, 5% are defective. Machine B, of the items it produces, 3% of them are defective. Machine C, of all the items it produces, 1% of them are defective. If you are given a defective item, then what is the probability that it came from machine C? Now let A be the event that the item came from machine A, B be the event that the item came from machine B, and C be the event that the item came from machine C. Also, let E be the event that the item is defective. So this is my evidence right here. Here we have to determine the probability that the item came from C such that it was defective. Well, the formula that I'll use is Bayes' theorem right here. This is nothing but this right here. I'm just substituting my A for C. That's all I'm doing. Okay, now in order to solve this, I need to know probability of C. Well, that's given to me. That's right here, 40%. The probability that item came from C is 40%. I also need to know this right here. This is my probability that the item is defective given that it comes from C. Well, that is 1%. That's also given to me. Now, the denominator is not given to me directly. This is the probability that the item is defective. We can determine that using the law of total probability. I know that my item that is defective, it can come from A, which would be this part right here. It can come from B, which is this part right here, or it can come from C, which is this part right here. These are my overlapping regions. So the probability that your item is defective is equal to probability of this region right here, which is the probability of my A and E. In other words, probability that item was produced by machine A and it was defective, plus the probability of this region, which is probability of B and E, which is same as saying probability that the item came from B and it was defective, plus probability of this region right here. That would be probability of C and E. This is my law of total probability. Now I can substitute values for each one of them using my multiplication rule. So applying your multiplication rule to the first one, you get PA times probability of E given that A. Same thing with the second and the third terms. All right, now let's calculate probability of A. The probability that the item came from A is 25%. That's given to me right here. So I know this. Now this one, probability of E, given that your item came from A, is 5%. That's also given to me right here. Okay. Now the probability of B, which that means the probability the item came from B, is 35%. That's also given to me right here. Probability that the item is defective, given that it comes from B, which is this term right here, is also given to me, is 3% right here. Okay, I got this. Same thing with probability of C. The probability that the item came from C is 40%. That's also given to me. And probability that the item is defective, given that it came from C, is 1%. That's also given to me. So all these values are given, plug in your numbers, and the answer is 0.027. So now I know my probability of E. Substitute your values in your probability of item came from C, given that it's defective, and your answer will come out to be 0.148. So after seeing the evidence, the probability went down from 40% to 14.8%. If you recall, the probability of C, that the item came from C, was 40%. Now it saw some evidence, and based on the evidence, probability of C, given that the evidence is seen now, is 14.8%. So it went down.